Okay, so that's good. Oops. Okay, so yeah, so again, last class we went through many examples of using semaphores for solving some typical synchronization problems. Specifically, we talk about using the semaphore as a lock, right? That would be a binary semaphore with initial value set to 1. We also talk about using the semaphore for managing resource allocation and use that for controlling concurrent access to multiple units of a particular resource, right? That's what we call, in its generic form, it is called counting semaphore. So usually you would set the initial value of counting semaphore to the number of available units of the resource, right? And then we also talk about using semaphores to enforce scheduling constraints, right? Or precedence constraints, where the semaphore is usually initialized to 0, and it is used to control or enforce the order of executing processes and threads. We went through a few examples of that. So then we apply these use cases to solve some classic coordination problems in the producers consumers problem, as well as towards the end of last class, we looked into implementation using semaphores for solving the dining philosophers deadlocks problem. All right, so now semaphores can be used for solving other classic coordination problems, like a readers and writers problem. That problem has very detailed description in the book. You guys can look into that, and we're not going to cover that in the class. And also the sleeping barber problem, if you guys have heard about that before. It's a very interesting coordination problem as well. So yeah, if you are interested, you can just, you're more than welcome to look into that in the book. All right, so yeah, we have concluded the semaphores. So we didn't really talk about the strength and the weakness of the semaphores. The semaphore construct is, well, it is far more superior than a simple lock, right? Semaphores could serve for multiple purposes. They're flexible, powerful. However, again, they're sort of hard to use. Okay, so there are some inherent problems with semaphores. So the way how semaphore operations work, the way signal those two operations, one could easily make mistakes in using them, right? So, we talk a lot of examples, talk about a lot of examples that I just talk about. So those examples, actually, we talk about, there are still simple programs, okay? So imagine with a complex setup, your assignment 5 programming portion is a little complex, a little more complex than what we discussed in the class. But imagine you have some more complex setup with multiple processes accessing multiple types of shared resources. Each resource access is controlled by a semaphore. So if you have so many processes, you have so many different logic for controlling access to multiple resources, the programming logic can easily get very complex. That could easily result in programming problems, right? So the problem with semaphores is that there is essentially no control of proper usage. Okay, so essentially you're just using the wait, the signal, right? Those two primitive operations. Basically, you do decrement and increment of that semaphore integer for tracking, right? For tracking the number of available units of a resource, right? But if a user doesn't use the up or down or wait or signal operations appropriately, we can get into deep trouble. Recall the problem just very quickly. We discussed with in the producers consumers implementation using semaphore, right? If we switch, the wait operation on the mutex and the wait operation on the buffer availability semaphore, remember, if we switch the order of those two wait operations on the mutex and buffer availability semaphore, we could end up with deadlocks, right? So the problem there is that there is no linguistic connection between semaphores and the data to which they control access, right? So you as a programmer, you have to specifically, design, implement your logic to trace essentially that integer for the semaphore to make sure that you do that properly, right? And also semaphores, they're essentially like shared global variables. That aspect is also not ideal. So with all these problems I just described, a higher level programming construct, maybe we need another more sort of readable or more understandable kind of programming construct than the semaphore. So we need to use another sort of a higher level programming construct to see if that can do better than the semaphores. So so we need to introduce this this programming construct named monitors. So they're like in 1974, 75, there were two computing scientists. They actually independently proposed an abstraction called a monitor, respectively, to make synchronization easier. Tony Hoare and Brinch Hansen. So I believe Tony is a British computer scientist, and Brinch Hansen is from Denmark. All right, so let's see how the monitor works. So a formal definition would be a monitor defines a lock, like a critical section. It defines a lock and 0 or more condition variables for managing concurrent access to shared data. Now we will get into the condition variables later on. Let's first look into the lock perspective. All right. So in its programming form, a monitor is similar to a class. Okay, like what you learned in any object-oriented programming, right? So what is a class, right? In the OOP programming, right? A class is essentially it's an abstraction that would tie the data operations together, right? And so here, a monitor would actually, in particular, it would tie the data and the synchronization operations together. Okay, so first, as as I said, a monitor is similar to a class in terms of its definition. So it needs to encapsulate the data that here we can view this data as shared data, right? Okay, so first a monitor would encapsulate the data that can be used by only one process at a time. Okay, so essentially the data encapsulated in a monitor can only be accessed and manipulated by the functions of the monitor, one process at a time. Okay, so so as I have here, as I have a small picture here. So here, right? So essentially, a monitor itself, all the operations, like, you know, as I said, monitor is like a class, right? Class has data and operations. All the operations in a monitor, they are all like critical sections, okay? So whenever you execute anything inside an operation of the monitor, that operation is a critical section, so that, you know, all the data of the monitor, when the data are being accessed inside an operation of the monitor, is essentially the operation itself would provide that critical section for accessing the data encapsulated in the monitor. Okay, so a monitor guarantees mutual exclusive access to the data it encapsulates. Okay, so that means only one process or one thread may execute a given monitor's methods at a time. Okay, so again, these methods in the monitor are critical sections that operate on the shared data. All right. So, so obviously, you know, when a process attempts to access a monitor function, if no process is currently active in the monitor, then the function call executes, right? But if there is already a process inside, already a process on the monitor, right? The process is, you know, if other processes want to access the same operation on the data, other processes will be blocked and placed on a queue. Okay, and upon leaving the monitor, the next process is allowed to enter the monitor. Okay. Any questions about the setup of a monitor? All right. So so we just talk about, okay, so all operations in a monitor, they're sort of like critical sections, right? Protecting concurrent access to the shared data the monitor encapsulates, right? But let's just refresh a little on what we learned from semaphores, right? So with semaphores, whenever whenever a process tries to access a shared data, it would do what? The process would try to check if a resource is available, right? Before entering a critical section to access the data, right? So in the semaphore case, in using the semaphore case, you would use the semaphore to do a wait operation, or you want to decrement that semaphore to see if that semaphore is still equal or greater than 0, right? If that's the case, you know the resource is still available, right? Then you can try to access the data. So here, I just talk about entering the critical section in the monitor, right, to access the data. But what if after you enter the critical section, an operation in the monitor to try to access a shared resource, what if that resource is not available, right? So basically you enter the critical section and you find out that resource is not available. So what are you gonna do, right? So in the, let's just quickly look at an example here. So this is again, producers and consumer problem. So in the insert operation, right? So here we have a monitor, okay? So entering the and when the process enters the enters an operation of a monitor, it would acquire a lock, right? That will make this whole operation as a critical section, right? After that, then this operation may find that, okay, you know, the in this case the bounded buffer is full, right? So you want to insert an item to that buffer which is full, right? So then what are you gonna do, right? So basically at this point, you may want to just block the process, right? Or the thread, right? Wanting to insert this item to the buffer. But but inside the critical section, right? If you block the thread or the process trying to access the shared data here, and then put this thread or process to sleep, then what would be a problem here? What would be a problem here? Right, so here, right, you enter this critical section, right? Like I said, every operation inside of a monitor, it is a critical section, right? So once the process gains access to the critical section, if it finds, in this particular case, if it finds the buffer is full, and then it would not be able to insert the item to that buffer. And the normal case would be you need to block this thread, right? But when you block this thread or process and put this process or thread to sleep, and what's going to happen? But this process or thread has the lock, right? So essentially, you don't want to put this thread or process to sleep while it is still holding the lock, right? If you put the thread to sleep with the lock, then other threads cannot access this critical section anymore because that lock is still being held by this thread, right? So the question here is that how do we block a thread and put it to sleep inside a critical section, right? So here in the monitor concept is that when we put the thread here to sleep, we need to do what? We need to have this thread or process relinquish or give up the lock it holds to the monitor. All right, so it needs to give up this lock and it can go to sleep. Okay, so that's where we introduce this condition, what we call condition variable, to do that. All right. So basically, the condition variables, they're used to allow us to, to put a thread to sleep inside a critical section. Essentially, when you put the thread to sleep, at that same moment, you need to have the thread give up the lock, right? So putting the thread to sleep and having the thread give up the lock, these two things, they need to happen atomically. All right. So this is the this is how the condition variable works. So the condition variable also has two operations similar to semaphores, okay? One is wait, the other is signal. All right. So essentially, it's same sort of operations. Okay. But in this, we know in the semaphores case, calling wait may or may not block the process or thread, right? Right. When you call wait on the semaphore, it would decrement the semaphore integer, right? But only when the integer is less than 0, then you would block the thread, right, or process. But here in the monitor case, for the condition variable, if you call wait, okay, on the condition variable, it will always block. Okay, so that's the difference here. So semaphore tracks that integer, but condition variable, if you call wait on a condition variable, it will always block the calling thread. Okay? And on the signal operation, if the condition variable does not have any process or thread waiting, then the signal operation on the condition variable would do nothing. Okay? While remember in the semaphore case, we would increment the semaphore integer, right? But here it was the condition variable. If there is no blocked processes or thread on the queue, then nothing would happen, okay? But if there are some blocked processes or threads on a wait queue, one of them will be brought back from the wait queue to the ready queue. All right? Any questions so far? All right? All right. Okay, so essentially the condition variable, it maintains a queue of processes or threads waiting for a condition inside a critical section, right? So I won't repeat what I just talked about. So basically these two operations, I list the details on what they're doing, what they do, right? Wait and signal. Now, one thing is that we need to understand is that a thread must hold the lock to call these two operations. You guys got that? A thread or process must hold the lock to the monitor to be able to call either one of these operations. Okay? Because you need to have the lock, then you can call either wait or signal. All right? All right, so let's look at this piece of program we just looked into. So, so here, so we have this again, this producer logic. When a producer tries to insert an item, it tries to first it tries to enter the critical section, right, of this operation insert. Inside this monitor. Again, every operation in a monitor is a critical section, right? So after a process or thread gains access to this critical section, here, for this particular example, it would first check what? It would first check, okay, if the bounded buffer is full, right? If it is full, then it would do what? It would call this condition variable, okay? So here we define, here we define a condition variable named full, right? So here, when we call this full.wait, right? So as I just talked about, if you call wait on a condition variable, what's going to happen? It will release the lock of this thread or process that you know, and that this process or thread holds, right, to this critical section. It would first release that, and it would put that thread or process to sleep, right? But you need to do this. So this is what the wait does, right? By this condition variable, and it would do these two things: release the lock and sleep atomically, right? So if there is a again, so this is how you do it with the condition variable here, and this insert method at the end, it would see if before inserting, right, do you have any item there, right? If before inserting an item to the buffer, if there is no item in the buffer, that means you just added one item to the buffer. Then you want to call a signal. So this empty is another condition variable, right? You want to call the signal on that condition variable so that a consumer waiting to consume something from the buffer can be notified, okay? All right, so any questions about this? Pretty clear? Everybody following?
Yeah, following along.
Okay.
We're not gonna have to code anything like this, right? This is our last coding assignment.
Yeah, you guys wouldn't. Yeah, we won't have. Probably in the next assignment we will have one problem, regarding this. But it wouldn't be programming assignment. This would be just a questioning assignment.
Okay.
And of course, this could be showing up in the quiz. Okay.
For sure. Thank you.
All right. All right. Again, this is how wait operation works. Talk about that, and this is how the signal operation works. Now, the wait operation is kind of a simple operation, right? Again, it blocks the caller and puts the caller to sleep, right? So that another process or thread can enter the monitor, okay? But the signal operation has some tricky aspects, okay? So when you do signal, right? When you do signal, you may check, right? You would check the wait queue, right? To see if there are any processes or threads waiting on the queue, right? So that you can bring one from that wait queue back to ready, right? But there is one thing we need to be aware that, remember, this whole thing, this whole monitor is what? It's a critical section, right? So you cannot have two processes, right? Two active processes or threads in a monitor at the same time, right? Remember, we talk about this critical section, but how do we handle this? While you are the signal process, when the signal process calls the signal, right? It would wake up a thread from the wait queue, and that thread wants to enter this critical section, right? And so there needs to be certain mechanism there to make sure we don't have both the signaling process or thread that is still in the monitor and the awakened process or thread that wants to continue the blocked execution. Right? We don't want those two processes or threads, we don't want them to be in the monitor at the same time, right? So this handover process from the signaling process to the awaken process, we need to do something something special there to make sure that the signal process to hand over this lock to the awaken process properly. Okay, so how do we do this? So there are in general 3 different thoughts on what to do about this. Branch Hansen proposed that the signaling process or thread would be ejected from the monitor immediately when it hands over the lock to the awakened process or thread. Okay, so we're gonna like in your assignments that later if the problem, if we have a problem for this, you will assume this. Okay, you will assume that we will use this way, that when the signaling process hands over the lock to the awakened process, it would the signal process would be exiting the monitor immediately. Okay, so in this kind of setup, in other words, a signal statement may appear only as the final statement in a monitor procedure for this kind of for this kind of mechanism that proposed by Hansen. Okay, and another similar approach proposed by Tony Hoare was that so he proposed to suspend the signaling process or thread and let the newly awakened process or thread run. Okay, so both Hansen and Hoare, they propose something that we need to stop the signaling process right away, let the awakened process take over. Okay, a third solution to this would be the signaling process continues to run. It continues to hold the lock. Okay, the awakened process can only execute after the signaling process finishes its logic and leaves the monitor. Okay, and actually most today's operating systems, they use this kind of solution. Okay, we'll see how these different approaches, they work differently in the code. All right, this again, this is a recap of how monitor operates. Okay, basically I described this already in details. So let's look at this example here. So we come back to this example. So I just talk about how you use a condition variable to block a thread and put the thread to sleep, right? So here, see here how we check, we check this buffer, right? We use if here, okay? If buffer is full. Now this buffer here is what? This buffer here is the shared data structure, right? Buffer, bounded buffer, right? So we use if here, right? So if we use use either Hansen or Hoare style for exiting for the signaling process to exit, we can use if here, okay? But if we use a message style, which I just talked about, okay, this one, which most modern operating systems, they use this solution. We would need to change this check here using while. Okay? Can someone tell me why? Why we want to use while here instead of if for the message style? Okay? Remember what message style is doing, right? It would let the signaling process continue to run. The waken process can only execute after the signaling process leaves the monitor. Okay? So why in the message style we want to use while buffer.full here? Can anybody give me an idea? You guys know what I'm trying to talk about, right? So here the difference, what are the difference here? What are the differences here? So essentially both Hans and Hoare, they propose to have signaling process or thread give up the lock of the monitor to the waken process or thread immediately, right? Right? So the waken process or thread can take over the lock and execute its blocked execution right away. But the message style let the signaling process continue to run. Why in the message style here, we need to do this while loop here. Anybody? No? So, if the signaling process gives up the lock immediately to the waken process, right? So here, let's say, a thread is a process is blocked here, right? For.wait, right? If this waken process can acquire the lock immediately from the signaling process, then it would only need to check this buffer if this buffer is full once, right? You only need to check it once. Why? Because because you hold the lock, right? The waken process or thread would hold the lock, right? And the lock would guarantee no other processes or threads could mess up with this buffer, right? Because you immediately acquired the lock, right? While in the message style, right, the signaling process still holds the lock, right? And once the signaling process gives up the lock, you don't really know which, there were maybe other threads, right, that could be taking that lock from the signaling process and change the buffer, right? Before this blocked thread can eventually acquire the lock and execute, right? So this is why, that in the message style, you need to do this while loop here to check if this buffer is because you could have a situation that the signaling process gives that lock to another thread that other thread could have the lock and then enter its own critical section and then insert an item to the buffer that would make the buffer full again, right? And then eventually this blocked thread acquires the lock, and maybe this buffer will become full again, and this thread would be blocked again. It needs to wait for the buffer to become not full, right? Everybody is following what I'm trying to say? So for the message style, you need to use while, okay? here. Does this make sense? Yeah, anybody? Does this make sense? All right, so. Okay, and this is the other, this is cool. All right, thank you for the response. Okay, so this would be using, this is the other function, remove for the consumer, okay? I won't go through the details here. All right, so actually in the real world implementation, the Java library has internal support for the monitor operations. Actually, in fact, that every object, every class in Java inherits from what class? From the object class. Okay, that object class, that root class, that top class in Java, that class actually has internal support for monitor operations. Okay, so that means any class inheriting from the object class in Java would give you monitor capability. All right. So so let's quickly go through this example here. All right. So so here the monitor, we talk about the monitor. Every operation in the monitor is a critical section, right? So in Java, you use what? You use a synchronized word, okay? You use a synchronized directive. When you define your, declare your method, you use synchronized, that will make the operation of your method critical, as a critical section, okay? So that's the support from Java to make your method as a critical section. And here, basically the same logic here. So if you know, for this insert method, if the buffer is full, and then it will make this thread or process go to sleep. Okay. So here, how do you make it to make it go to sleep? You call wait. Okay. All right. And if here you at the end of the insert method, if you know this buffer, before you inserting this item, the buffer is empty. Now you have one item there. You want to notify the consumer that item is available now. So you call notify. Okay. So notify in Java, which notify is a public method, right? From the object class. That notify is working like a signal operation, we just talked about. Okay. And so this is with Java. So if you are using C++, it's a little more complicated, right? So because in C++ you don't have the synchronized keyword you can use, but you could explicitly provide the lock, right, for all your methods in the class. All right, so so again, this is a quick summary for the monitor. I won't go through the details here again. All right, so basically, you know, condition variable works very similar to semaphore, but as I already talked about, you know, the wait operation and signal operation, they are a little different from the wait and signal operations in semaphore, right? So let's take a quick look at as an example of, you know, what kind of difference between the semaphores and condition variables on those two operations. So let's start with this simple example here. So let's say we have a semaphore, right, with initial value of 0, right? And then you call wait on this semaphore, right? What's going to happen? When thread 1, right? Thread 1 calls wait, right, on this semaphore. What's going to happen to thread 1? Come on. Anybody? Let's do this exercise together. Thread 1 calling wait on this semaphore with initial value of 0. What's going to happen to thread 1?
It's gonna execute, and then the semaphore will be -1.
Yes.
Right.
Well, it's already with 0. Yes. Yeah.
Wouldn't it already
It'll
be
block.
blocked?
Right. So yeah, combining Amy and Alexei, your two responses, yes. So basically, yes, you would decrement this semaphore, right? 0 to what? To -1, right? And then after that, so remember the wait operation always does the decrement first, right? So after the decrement, you see this semaphore has a negative value. That means what? That means you don't have any resource available, right? Essentially because your semaphore integer starts with 0. So that means you don't have any unit of resource available. You decrement it, it becomes -1. Then you check on this integer, it is -1, it would be less than 0. Then thread 1 will be what? Will be blocked, right? Thread 1 will be blocked, okay? So you guys may want to do more exercise of this on your own, okay? I can guarantee this kind of stuff will show up in the quiz, okay? So, all right, so thread 1 will be blocked. Okay, so thread 1 will be blocked, right? And then you call thread 2, you call signal on the semaphore. What's gonna happen? What's gonna happen? Anybody?
It'll be incremented to 0, and then thread 2 will be able to execute.
Yeah. And what about thread 1?
And then thread 1, I don't know.
Okay, good try, good try. Well, actually, you kind of answered the question. So thread 2 calling the signal, and that means what? That means this, let's see here. Let's put -1 here for the semaphore, right? Thread 2 calling signal, then the semaphore will become 0 again, right? Once it's become 0, right? Remember let me, okay. Where is that? Oops. Yeah, so this is the wait operation, right? Yeah, I do recommend you guys to go back to the slides and look more into the detailed implementation of the wait and signal. So first you will decrement, okay? Then you will check this value. If it's less than 0, it will block the thread. And what about the up or signal? It will increment this value integer, right? If it's less or equal to 0, it will what? It will try to go to that wait queue to bring one blocked thread or process there back to a ready queue. Okay. So here. So here, when thread 2 calls signal, the semaphore becomes 0 again. Then thread 1, because thread 1, let's assume we only have 2 threads, right? in the system. So thread 1 is the only thread waiting on the queue. Thread 1 will be brought back to the ready queue, okay? So thread 1 will be unblocked. Unblocked, okay? Okay, so let's do this same thing using condition variable, okay? So as we talk about, if you use condition variable, you call wait, you will do what? It doesn't have any integer to track. It will always block, okay? And when thread 2 calls signal, it will do what? It will unblock thread 1, okay? Will be unblocked, thread 1. All right, so looks like these two, in this kind of sequence, semaphore and condition variable, they work the same, right? What about this? What about I call signal first, then I call wait. All right. In the semaphore's case, if you call signal, right, because you start the semaphore with 0, right? If you call signal, then the semaphore will become 1, right? 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 And then this is like, say, this is the semaphore case, okay? In the semaphore case, you call signal first, the semaphore integer will be incremented to 1. Then thread 1 calls wait. It will decrement the semaphore to 0. But it's not less than 0, so thread 1 will not be blocked, okay? So, but in the condition variable case, what's gonna happen? If you call signal here, thread 2 calls signal, right, with the condition variable, nothing will happen because what? Because even you call signal, there is nothing waiting on the queue, right? So this signal call will result in nothing. Okay, but if you call wait on thread 1, it will do what? You will make this thread 1 blocked, right? Remember? So essentially, you guys can see the difference, right? So here is sort of like the semaphore sort of has a memory of the history, right? The semaphore tracks this integer, right? And it would track the this integer, like it has its own memory, okay? The semaphore, while in the condition variable case, it does not have any memory, okay? You call wait, it will block the thread. You call signal, it will check the wait queue if there's anything on the wait queue. If there is one, at least one, it will bring that, bring one of the threads or processes on the wait queue back, okay? You guys all get the idea? Okay, so basically, yeah, semaphores, you can sort of you know, say semaphores remember history or states and conditional variables. They do not. They're stateless. Okay. All right, so that's basically we wrapped up the the topic for the semaphores and the monitors. Okay, so let's move on to the message passing. This would be the final subject of the inter-process communication. So the producers and consumer problems, we talk about, again, it's a classic problem of inter-process communication. So far, we have talked about using semaphores or monitors to implement solutions to the problem with what? With shared memory, actually, right? So there is a shared buffer, right? So that means, so the processes or threads, they need to be on the same machine, right? So they can access the shared memory, right? But what if the two processes talking to each other live on different machines? How are we going to enable them to be able to talk to each other? Well, we need to enter message passing. Okay, so obviously, not only message passing can be used for two processes living on different machines to talk. Of course, message passing can also be used by the two processes on the same machine to talk to each other. So let's see how message passing can be used for implementing the producers, consumers communication with no shared memory. Okay, so it turns out we have these two system calls we can use, send and receive. Okay, we can use to send message we can use send to send message from a source to a destination. And the destination could use receive to receive the message. All right, so if of course if no message is available, the receiver can be blocked until one message arrives, right? All right, so let's see. Let's first talk about some basics of the message passing. So here we need to define the source and destination, right? So in the diagram to the left, so here we have, let's see here, why I can't draw something here. Okay, so here, so this diagram is about direct communication, right? So two processes send messages to each other directly. The address parameters in the send and receive calls are the processes. Okay, remember we have this address here. Okay, for the indirect communication here on the right, so this describes a scenario that a sender and a receiver, they communicate through a mailbox, right here, the mailbox, or port ID. So when mailboxes are used, the address parameters, when I talk about the address parameters, I'm talking about this destination source, okay? So the address parameters in the send and receive calls are mailboxes, not processes, okay? So note that with indirect communication, it is possible to have multiple readers or writers to the same mailbox, okay? You can have multiple ones here. All right, so this is like a two approaches, right? So when we actually implement these two approaches, we could run into some implementation issues. So how the issues are, how does one name the processes or mailboxes uniquely, right? So we need to solve that. And when they communicate with each other, how does one authenticate the messages to ensure that no other processes fake or pretend to be the sender, right? And another issue would be what happens when messages are lost or corrupted during the message when the messages are on the route from the sender to receiver. What if the messages are lost or corrupted? So these are essentially we need to look into these implementation issues. Let's first look into the delivery. So how can we come up with some schemes that we can guarantee reliable delivery, right? So obviously reliable messaging delivery is an important subject in inter-process communication, especially over the network, if they're communicating over the network. So so there are some basic ideas, right, to address the lost message deliveries. So the basic idea I put here is that the receiver can send back some acknowledgement, right? If it receives the message from the sender successfully, right? So you could, the mechanism could work, if the sender does not receive acknowledgement from the receiver within a reasonable amount of time, then the sender would retransmit the message, right? But however, there is a tricky scenario that may make this a little more complicated. What if the receiver receives the message successfully, and the receiver acknowledges the message to the sender, right? But that acknowledgement gets lost, right? Let's say the receiver receives the message successfully, and it tries to acknowledge the receiving of that message back to the sender, right? But the acknowledgement itself can get lost, right? So in that case, the sender eventually will retransmit the message again, right? And then the receiver would get a duplicate message, right? Because of this retransmit, right? So how should the receiver process that duplicate message? Well, one way to handle that is that the receiver could do is it could use some kind of information, right, from the message, either a sequence number or let's say a checksum, right, to uniquely identify that message. Or to differentiate between messages. So if the receiver receives a duplicate message, the receiver would know, oh, okay, I already got this message before, now I got to retransmit. If that's the case, it could just discard the duplicate message. All right? So because the networking could be, the communication over the network could be asynchronous, right? Over an unreliable network, a lot of complicated scenarios could arise. Of course, that would be the study of the computer networks. The study of computer networks deals with how to communicate reliably in an unreliable networking environment. And that study would deal with how to address the issues from unreliable message passing. All right, just want to give you guys some quick examples of messaging problems in an unreliable networking setting. All right, so reliability is one aspect of the messaging. So another aspect is what? Is the message passing efficiency, right? Especially over the network. So the efficiency part, yeah, we won't discuss about that aspect in this class. Also, there is also the security side of message passing. We won't discuss that either in this class. So if you guys are interested, you can just look at the textbook, and there are some details there. All right, let's quickly go through some. The buffers that related to message passing scheme. Okay, so in the bounded buffer problem, in the producers and consumer problem, we talk about the bounded buffer, right? Is a shared memory, right? Shared piece of memory between the two processes and threads that live on the same machine, right? But here, like, you could have the two parties on the two ends of the message passing, they could live on different machines. Does that mean we don't have any buffer between them? Turns out there's still a buffer in between the sender and the receiver, right? In the direct communication scheme, it is a buffer actually maintained by the operating system, right? So if the sender sends the messages faster than the receiver can receive, the messages that were sent but haven't been received by the receiver would be put into a buffer, actually, but that's handled by the operating system. You just need to, the sender just needs to call send. The receiver just needs to call receive. Remember those two system calls I just talked about? So there is a buffer maintained by the operating system between the sender and the receiver. Okay, so this buffer will not be accessed directly by neither the sender process or the receiver process. Okay, in the indirect communication scheme, remember that mailbox I just talked about? The mailbox serves as a buffer, right, for communication between the sender and the receiver. Okay, so the next question would be, okay, so if there is still this buffer between the sender and receiver, how large would that buffer be, right? You know, like, I mean, again, we're talking about the coordination between the sender and receiver, right? You know, you can't send a lot, you can't send the messages that are bigger than the buffer can hold, right? If the receivers cannot consume the messages fast enough, right? Eventually, you still have a buffer overflow problem if you send too many messages, or you could have a buffer underflow problem if your receiver consumes the messages faster than the sender sends the message. So how do we maintain that buffer capacity? Okay, so there are a few options here, and they are actually used for different use cases. Okay, so one simple way is you keep that buffer as empty, right? That means there is no buffer between the sender and the receiver. In that scenario, it's sort of your message passing or sending is kind of is synchronous kind of operation, right? Synchronous operation. That means the sending process blocks until the receiving process reads the message. Essentially, you have to, you know, the sending process sends a message until the receiving process reads that message, the sending process would block. So essentially, there's no buffer between them. It's a direct sort of, the message is directly copied from the sender to the receiver, right? No buffer between them. So they're sort of like the sender and receiver, they're kind of forced to run in lockstep, right? They have to be synchronized with each other. So that in a French word is called rendezvous, right? So it's sort of, this actually kind of, this mechanism is kind of used for remote procedure calls. It's sort of like a synchronous remote procedure call. All right. So the next mechanism would be bonded buffer, which is a finite kind of length queue. So this works just like the bonded buffer we talk about in the producers and consumer example. If the sender is faster than the receiver, it would eventually block, right? If the receiver is faster than the sender, it will also eventually block, right? And then you have this unbounded scheme. That means it's sort of, the communication is always asynchronous. Theoretically, you have an unbounded queue that would hold the buffer between the sender and the receiver. All right. All right. So I won't go through we need to conclude the class today. So essentially, you can use send and receive system calls to implement the producer and consumer problem. Like for the scenario that the sender and receiver, they're living on different machines. So essentially, this implementation is pretty straightforward. You just need to call the send and receive, okay? The producer would call send, the consumer would call receive. And the buffer I just talked about and the communication between the sender and receiver, they're all being managed by the library and the operating system, okay? All right, this is essentially the last slide of the inter-process communication topic that we need to discuss in this class. All right, that's pretty much it for the inter-process communication. All right, any questions before I end this class today? Everybody following? Everybody feeling comfortable about inter-process communication? All right, cool. All right, so excellent. All right. Okay, so I will end the recording first.